Okay. All right. So good afternoon, everyone. So we've spent, almost two lectures talking about one particular phase of matter, which is the Z2 spin liquid, and we're still not done. I'm going to summarize what we've done so far, and then say a few more things. But there's a reason for spending so much time on this, because I hope to show you today that once you understand this very basic example of fractionalization, you can build very rapidly with a few more tricks, essentially the complete library of phases, fractionalized phases that have been seen, in experiments. So this includes the fractional quantum Hall states, possibly some non-abelian spin liquids, and so on. So we'll make a library of all these phases, and you'll see, hopefully, by the end of this lecture today, how to just build them up in a fairly systematic way. But let's just, first part, let me summarize what we've done so far. So the main claim so far is that the low energy physics of phases of matter, which are in this what's called the Z2 spin liquid, that their low energy physics of the excitations are described by this pure Z2 gauge theory. So this is a very old model known in the lattice gauge theory literature for many, many years, originally introduced by Wegener in the 70s. So here I've written it in sort of a modern language in the quantum formulation. So you could take any lattice, any two-dimensional lattice, but we'll take the square lattice for simplicity. And every link of the lattice, there's a qubit sitting on the middle of the links. And for each qubit, there's the Z and the X operators. And you take, this is the simplest Hamiltonian that you can take. You take the product of Z's around a loop. That's one term with coefficient K. And just an X term on every loop. Now, the logic behind these terms is that all of these terms commute with a certain operator. And this is the operator that generates the Z2 gauge transformation. It's the product of the X's on all the links around the site. Okay. So, and the important point is this G commutes with this operator. It obviously commutes with this, but it also commutes with this because every G has an even number of overlaps with the product of Z's around the loop. And then you can add many more terms if you want, as long as they commute with the G, they're all legal. Okay, so we're going to say a bit more about the properties of this theory. But this theory, in the limit of small little g, has a phase of matter, which is a deconfined phase of matter with fractionalized excitations that we're trying to understand. So we got this theory in two routes. One, we started with the seemingly ordinary XY model. And I made this decomposition here of the unimodular field of the XY model in terms of field H, which will now be a Higgs field, and e to the 2I phi. So this decomposition has a U1 gauge invariance. And so you could rewrite the XY model as a U1 gauge theory. But then we go into phase D, that's what I called it, where you condense this field H. So you just condense it. And then we argued that in that limit where you condense H, you could replace the U1 gauge field by a Z2 gauge field, Z. And now I'm writing it not in terms of sigmas, but in terms of these quantum information type operators, capital Z equals plus or minus 1. Then the final theory for this phi, this bar phi, in the quantum language, which I haven't written down so far, but here it is, I wrote it down in the classical language. So now this is a two-dimensional classic quantum model. One term here is just the same HZ2. And then you have this cosine terms of half angles here. But then to make this gauge invariant, there has to be the Zij factor. That came from the original, this factor in the original U1 gauge theory. Now also the time-dependent part, the time-temporal part of this, I've written now as a kinetic energy, where L is just the angular momentum associated with this phase phi. Okay. And now this also has an operator on every site that commutes with the Hamiltonian. It's the same G operator over there, but now this particle phi also has a Z2 gate charge. It's just -1 to the angular momentum. And it's easy to check that this commutes with this Hamiltonian. All right, and then this is the part we didn't prove earlier, that this has to be equal to a certain value that I'll now explain why. All right, so then we looked at the antiferromagnet and we followed almost exactly the same route, although the formalism is a lot more messy, there's more indices, the geometry is more complicated, but really all we're doing is very similar. So we took the spin operator and we decomposed it in terms of Schwinger bosons. And that immediately meant there was a U1 gauge theory, which you can write down as a path integral. Then we looked for saddle points of the U1 gauge theory, and we found that under certain conditions, there'd be a certain Higgs field that likes to condense. That's this QIQ field, which is a pair of bosons. So you have some bosons, they pair up and they condense. And this condensation of Q, this Q here condensing, is exactly the same as the H condensing here. And H, had a U1 gauge charge of 2, if you remember. And so does Q have a U1 gauge charge of 2. So in the end, when you look at the gauge fluctuation, and this is to answer the question in the beginning, you don't have to worry about the photon. You can just reduce it to a Z2 gauge theory. And the fluctuations of Q, just like over here, you can replace the fluctuation of Q by just the fluctuation of the sign of Q, which would be the Z object. Now, there's one important caveat here. Even when you condense this Higgs field, sometimes the U1 gauge theory is not fully broken. And that happens on bipartite lattices, on the square lattice with nearest neighbor interactions. Then even when you condense a boson pair operator, even though it has charge 2, it seems like it has charge 2, it's actually neutral under a staggered charge. When you put one sublattice with one charge and the other sublattice with the opposite charge. So in that case, you do get a photon, and you do have to do a U1 gauge theory. That's also a very interesting thing to study, but it doesn't lead to a gap spin liquid state. So that would be another set of lectures. We won't talk about it. We look at the case on a non-bipartite lattice where this condensation of this boson pair just breaks the gauge symmetry completely down to Z2. Not completely, down to Z2. And there's no more U1 to worry about. And now we can write down our full theory, which is similar to this theory here. We have these bosons, which are the spin-ons. These B particles are the analog of e to the I phi. And as they move, they have to pick up a factor of the Z2 gauge field. And there's a constraint, and then there's HZ2, which is the model right here. So these two theories describe both the spin-ons and the bosons of the Z2 spin liquid. That's the complete set, the complete Hilbert space. But when you're deep in the Z2 spin liquid phase, and the spin-ons are very heavy, very high in energy, which are the B particles or the phi particles, then you can ignore them and you go back to that theory, which is what we'll study in a few minutes. Finally, if you look at this Hamiltonian, this is a Hamiltonian for the Z's and the B's. As this also has a gauge charge that commutes. Again, it's the same X operator times -1 to the number of bosons. And now you see where this -1 to the 2s comes from. So if you want to go to a theory where we forget about the boson fluctuations, we should, of course, do it where we impose the constraint that B dagger B is 2s. That was the constraint that required this thing to transform as the spin S. And so the GI becomes not 1, but -1 to the 2s. All right, so that's a summary of all the things I've talked about, and I'm happy to entertain more questions.
When we use the Springer representation to go from a spin model to the Springer bosons, normally
Yes.
I would guess that the new Hamiltonian would have a contribution from a kinetic term for the imaginary direction, an imaginary versus Zumino term, and a quantum Hamiltonian. Is this right? But where do I see this in this antiferromagnetic Hamiltonian you have written?
Well, there is these bosons. This is the Hamiltonian, but the bosons have the usual commutation relations, B dagger equals 1. And so if you write that on the path integral, of course, it's a term like, that's a term like B dagger dB d tau. So that's certainly there. We keep that. It's just in the commutation relation of the bosons. It's on the lattice.
Yes, and the constraints from the Lagrange multiplier term, in what does it correspond?
That's also over here.
Yeah.
So that I've made time independent, and you can always choose the temporal gauge where the Lagrange multiplier is time independent. So in going from here to here, I'm using some temporal gauge where the time component of the gauge field I set equal to 1.
And what can I regard as the best Zumino term, or isn't it in this formulation?
So it depends what you mean by a best Zumino term. So the simplest best Zumino term is for a single spin. If you have a spin on the surface of a sphere, and it's fluctuating in time, just a single spin, then the simplest Zumino term is this term, AS ds d tau, which just computes this area of the spin precessing on the sphere. But this term is exactly that term, in fact. So you could rewrite, okay. So there's an exact identity that, Yeah. This integral over ds delta of s squared minus 1 e to this term, e to the a of s dot ds d tau. So this is the best Zumino term of a single spin with some Hamiltonian for the spin. This is exactly equal to integrals over dB, d lambda, e to the b dagger dB d tau, plus I lambda times b dagger b minus 1, minus the Hamiltonian of the spin operators. So this very familiar coherent state term is exactly the best Zumino term of the spins once we impose the constraint. So on the lattice, there is, of course, a best Zumino term, which is just the fact that captured by this. Now, there's a separate question when you go to the long wavelength limit and you have some continuum field theory, there's some higher dimensional best Zumino terms. In this model, no, they don't appear. In fact, the remnant of that best Zumino time anomaly is exactly this constraint. This constraint that GI equals minus 1 to the 2s is like the Z2 gauge theory version of the best Zumino term. In fact, if you take the full best Zumino term and you break it down to Z2, that's in fact another way to get this result.
Thanks a lot.
Sure. Other questions?
I have a question.
Yeah.
You called this Z2 spin liquid.
Yes.
I apologize if I missed something, but why this is a spin liquid? Because of the
spin liquid? Sorry?
Why this is a Z2 spin liquid? What makes this a Z2 spin liquid? Or a spin liquid per se? Doesn't matter.
Well, it's a spin liquid because the spin correlation functions there's no long range order in the spins. Spin correlation functions actually decay exponentially in this phase that we're going to talk about, in the deconfined phase. So, and it's a quantum system. So you could call it a quantum paramagnet, but that's not a fully descriptive term because they can be quantum paramagnets like a spin ladder, which has only integer spin excitations. So this is a quantum paramagnet that has half integer spin excitation. That's the preferred term, I think. It's called, these B alphas, or Bogoliubov rotations of these B alpha carry spin a half. So it's a spin liquid because it has no long range order and it has half integer spin excitations.
Okay. And a follow-up question would be,
and why is it Z2? Sorry, I didn't answer the other part. Why is it Z2? Well, because it's described by a Z2 gauge theory, and the spin-ons carry a Z2 gauge charge.
Okay, very good. Okay, now another question would be, I don't know, actually, I never learned this, but I heard about current states for spins. Like you can construct like a path integral using spin operators.
That's what I just erased. That's the current state path integral. Yes.
Yeah, but you use it there to construct the path integral, the current states for bosons, right? Because you transform spin into bosons, Schrödinger bosons. I'm saying, yeah, do you need to do that if you use spin current states or not? Or
you could, I mean, in principle, you could write this down as a path integral purely in terms of spin coherent states. You certainly could do that. And that's in fact how a lot of the early work was done. And that leads to various nonlinear sigma models for the spins. And then you have to look at monopole defects in the spins, hedgehog defects, and their Berry phases. It becomes a rather complicated business. And there's no easy way to use that approach to write as a Z2 gauge theory.
Okay, so you lost a little bit of this physics. At least it's
no, we've not lost it. No, absolutely not. Okay. So you could do it. I mean, historically, that's how it was first done. You start with the coherent state of spin. That's what Haldane did in the early 80s. And in 2 dimensions, if you try to play with it, you end up with these complicated Berry phases of hedgehogs. There were some papers saying early on there was Witten term. Those papers were just wrong. And Haldane was right in focusing on the Berry phase of the hedgehogs, but you didn't know what to do with it. Mm-hmm. However, once you take the coherent state path integral and rewrite it as a boson coherent state path integral with a constraint, which is what I'm doing here, then you figure out what to do. Then you find there's 2 possibilities. One is the U1 gauge symmetry is broken to Z2, which is what I'm describing. And that leads to the Z2 spin liquid. The other, where it's not broken, it remains U1, then you get all of those monopoles, Berry phases, Witten terms, and that's a whole long story, which all is, it's still in some ways ongoing. Not everything is understood about it, but it's not something I'm discussing.
Okay.
Because it does not lead in the end to any spin liquid phase. It may lead to spin liquid critical points, some conformal field theories, but it doesn't lead to the kind of simple gap spin liquid phase I'm talking about.
Okay, good.
And advertising for my book, there are many chapters in my book that will describe that. But so I won't.
Maybe I should buy the book.
Yes. Not out yet, but yeah, soon, I hope.
Thanks.
Okay. Other questions? Okay, so now that I've summarized and you're all on the same page, I hope, let's just talk about this theory, okay? Here's our theory, which, you could just imagine was just given to you. But in fact, hopefully I've convinced you it's a very physically relevant theory for many systems. And let's try to understand this theory as a function of, you can put k equals 1 if you want, for small g and large g. And the beautiful thing about this theory is quite easy to analyze, both at small g and at large g. And you get some rather very different physics, and then it's very clear what's going on. So we're going to draw a line here, say g over k, they're both positive. It's known that this theory has some critical point, and really this particular theory is extremely well understood, at least from the square lattice. So this is 0 here, that's some GC. And for small g, we will have the Z2 spin liquid, the deconfined phase. Which will be the Z2 spin liquid. And I have lots of interesting properties, and I could spend the next 2 lectures just describing those properties, but I'll just focus on 1 or 2 here. And at large G, there's the confining phase. And this will be at least trivial, will be the trivial phase that we're not interested in for integer S. And what it is for non-integer S, well, let me just, for half integer S, let me leave that as a suspense for now. It's something different. In fact, for half integer S, there's now a theorem. It goes back to Lieb-Schultz-Mattis theorem in 1 dimension. There's a Hastings-Oshikawa theorem in 2 dimensions. That under certain conditions, half integer spin antiferromagnets cannot have a trivial ground state. And that, fortunately, is obeyed by this theory. And again, this constraint is really crucial for that. Okay. So first, let's just take the simplest case. So I'm going to focus on this regime now. And let's just think about what is the ground state and what are some of the excitations. So let's just start with G equals 0, where already things are quite simple. So at G equals 0, that term isn't there. You just want to make, you want to take a state, which I'll call all spins up, which is just product on all the links of the spin up state. So if I take the state, then this just gives you 1. It's an eigenstate and has energy minus k. So on every plaquette, and so it's it is one of the ground states. But the only trouble with this state is that it's not an eigenstate of G. I want to make I also want my ground state to obey. I want my ground state to obey that Gi as an operator acting on the ground state, whatever it is, should be -1 to the 2s times G. So that should be my actual ground state. Okay, so this doesn't obey it with all spins up, but it's very easy to fix it, actually. So the actual ground state will be G. So this G should not be confused with this G. Maybe I should use some other symbol here. Let me call it little g. No, there's another little g, sorry. I'll just stick with G and try to put a hat on the operator. Okay, so the actual ground state, it's easy to write this down. It's product on all links and 1 plus -1 to the 2s of G hat on every site, so product on every site, sorry, acting on all spins up. So first of all, it's easy to check this as an eigenstate because the G commutes with this term, so it doesn't do anything, you can just take it right through. And then it's also easy to see that it obeys this, it's gauge invariant. Because if you hit Gi on this, you're going to get exactly that. All you have to use is the fact that Gi squared is 1. So it's the product of X operators on 4 links and squared is 1. So once you use that, you can see this is the ground state. So what does this look like? Okay. So here's my lattice. So the state here is that all spins up. So when spins are up, I won't write anything on that link. So this is the state with all spins up. Now, if I hit a G, so I have a term here when I expand this out. I say on site I, I'm going to hit G on this state. Well, that has 4 x's, and it's going to flip the spins on those x's. So every time I hit a G, I want to denote that by a closed loop like this. And this tells me that this spin is down, this spin is down, this spin is down, this spin is down, this is down. So you can see every G just introduces a loop. So for example, if I hit the G on this side, that's just going to grow the loop like this. And you could also hit it here and so on. So you can see that this is just equal to sum of various terms like this. That's all closed loops. So this, it's just the sum over all closed loops. Times, because of this -1 to the 2s factor, and -1 to the 2s times number of plaquettes. All right, so that's the wave function. It's just, it's not just one state, which is already quite non-trivial. It's the sum of an infinite number of terms. And it's the sum over all plausible closed loops. And now you're trying to see the flavor of, are we becoming here? It's not just one state. It's the sum of all complicated different configurations with some phase factors between them. All right, so that's the ground state. What about the excited state? So the property of this state is that if I look at the product of z's around any loop, if I took the product of z's around any loop, it's always +1 because the white loops will always intersect an even number of red loops. Okay, so you get +1 here, -1 here, the product of the z's is still +1. So that's why, and you can add any loops on the dual lattice. These are all closed loops on the dual lattice, not on the regular lattice. Okay, all right, so that's the ground state, sum over all closed loops on the dual lattice. All right, what about the excited states? Well, the excited states are precisely the M particles of the Wisons. That's how we constructed it. So the excited state would be something like this. Suppose I flip this spin. So I take an open line. So I take a line here and go from here to there. Instead of having a closed loop, I have one open line. So this means I flip the spin here, flip the spin here, here, and here. And now I have to pay an energy 2K for this loop because it's -1, 2K for this loop because -1, and that's it. So this is a state with two Wisons. With one Wison here and one Wison here. And then of course, to make it gauge invariant, I have to sum over all loops. I can put loops in there and sum over all of them, and that's it. And so this will have energy above the ground state. It's a two Wison state minus the ground state. You pay energy 2K over here, and you pay energy 2K here, which is 4K. And now I leave it to you to do perturbation theory. There'll be corrections about a G over K, which can be quite easily worked out by looking at the effect of the neighboring terms. So, and in fact, what will happen at order G is that this Wison will start moving around. It'll get some effective mass. And I think the notes work out what the effective mass of the Wison is. You can all compute it. And if you feel like it can go to even higher order, any order you want in G over K, and compute it with not too much difficulty. So that's the basic structure at very small G over K. You just have a unique ground state, which obeys this. And above the ground state, you have these Wison particles, which have a certain gap and a mass. You can compute the dispersion. The only feature is that any local operator, which is unusual, any local operator can only create pairs of Wisons. It cannot create a Wison on its own because this line has to have two ends. A line can have just one end. All right, so is that all very clear? Any questions? Okay, so then the most interesting properties of this state appear on a torus, and that's say a little bit about. So the topology comes in a very interesting way. And this is something that, for whatever reason, was not understood in the early days of lattice gauge theory. People weren't thinking along this language, but that really is actually the best way to distinguish the two phases over here. Okay. So let's put the system on a torus with periodic boundary conditions. So here I imagine I have a torus where this end is the same as this end, and I have my square lattice. And then I ask about the ground state on a torus. All right. So what I've said so far is that the GI commute with the Hamiltonian. In fact, I can make a stronger statement that the GI and the product of all the GI completely exhaust the set of operators that commute with the Hamiltonian. So this, you take G1, G2, G3, G4, and so on. You can make all kinds of products and sums of these GI operators, and they all commute with the Hamiltonian, since each of them commutes with the Hamiltonian and they commute with each other. However, when I put it in a torus, you find that's no longer true. There turn out to be two more operators that commute with the Hamiltonian. And I'm going to call those operators Vx and Vy. Commute with HZ2. And these operators are not just products of the G. And what are these operators? Well, it's again, you take sorry, I have to make sure I get this right. You take the product of the x's excuse me, I always get confused whether I should put it in the direct lattice or the dual lattice. So I don't want to make a mistake. Let's go back. Here it is. Oh, okay, you do take the direct lattice, dual lattice. Yeah, here they are. Okay. Yeah, all right. So you draw this red line that I was drawing earlier, and where I had the x operators, and I take a line, whoops, that's not periodic. Take a line that just goes around the torus. So here's some line that goes all the way around the torus. And I define V sub x is just equal to V sub x is just the product on this loop here. Let's call this Cx. Some loop that encircles the whole torus of the x operators. So you take x here, x here, x here, x here, x here, and x here, so on. And now it's easy to see that this also commutes with the Hamiltonian because, well, any plaquette on the original Hamiltonian will cross this line twice. So there's a plaquette here, a plaquette here, plaquette here, and the others don't cross it, so they obviously commute. So this also commutes with the Hamiltonian. And similarly, I can draw another line in the y direction, something like this, could be any line you want, and that will also commute with the Hamiltonian. Now, it doesn't matter where you draw the line, because you can take the product of the V's and the G's to move the line around. If I put a G operator on this plaquette, it will just straighten the line. Put it over here, it will go here. So you can go anywhere you want. So this, taking the product of the G will just move the lines around. And so now the commutant of the Hamiltonian is the product of all the G's and the product of all the V's. That's the complete set of operators that commute to the Hamiltonian. There's two new operators that come up, and they only come up when you have periodic boundary conditions. If you have an infinite system, there's no way to define them. Okay, because there'll be things at the edges that will lead to some problems. Okay. So now I can ask, what is the ground state on a torus? And now we come up with the remarkable result that the ground state, which would seem like non-degenerate before, is just a unique state with the lowest energy. But now you're going to get a fourfold degeneracy. There's a topological degeneracy, and that's the key. That degeneracy is the key to all the ideas on using the spin liquid for quantum topologically protected quantum computation. Okay. To see that, I mean, there's many easy ways to see that. But one way is to define another set of operators, which I'll call the W operators, which do not commute to the Hamiltonian. But let me just define them because they're convenient. So we define Wx and Wy, and these will be products of L belonging to some other contours. Let me call them D contours of the Z operators. And similarly, Wy will be product of L belonging to the D contours of the Z operators, of the dx and dy. So what are these D contours? Well, the D contours are contours on the direct lattice. That's why I call them D. So I could just take the simplest one, which is the straight line here. So that's a contour that encircles the lattice, and that's the contour dy. And I can take another one here, which is dx. So I have these four global operators that act on operators that go around the torus, on the cycles of the torus. So these are kind of like topological operators. And in the end, for those of you who know this, if you write down a very low energy topological field theory, the topological field theory is a theory only of these operators, the V's and W's. But right now I'm working with the full Hilbert space, not just the low energy limit. Now these operators are products of the Z's, and they commute to the Hamiltonian at little g equals 0. But once you turn on little g, they don't commute. So, but still they're very useful. And the reason they're useful is they obey a very nice algebra with the V operators. So now you can see that the D operator in the Y direction, the dy, intersects with Cx at an odd number of points, just one point here. And similarly with dx and Vy. So you can now check very easily that Vx Wy equals minus Wy dx, and Vy Wx equals minus Wx Vy. So these anti-commute with each other, and all other operators commute. So Vx commutes with Vy and Wx, but these crossed operators in the two directions anti-commute with each other. So you can think of Vx, the Wx and Wy as kind of raising and lowering operators in the space of the eigenstates of Vx and Vy. The square of all these operators is 1, so the eigenvalue is only plus or minus 1. All right, so now once you have these operators, the W's are just for convenience. They're only good, nicely defined exactly at g equals 0. But the V's commute to the Hamiltonian at all values of the coupling. So the ground state, all eigenstates should also be eigenstates of Vx and Vy. All right. So what is the ground state of the system? Again, let's look at g equals 0. So So at G equals 0, so the first ground state is still a ground state. G is just product. And let me put S, forget the -1, put S integer for now. It doesn't make much of a difference, so just save me some writing. 1 plus GI, let me call that the 0 state. 1 plus GI acting on all spins up. So this is also an eigenstate of the system. I mean, this is an eigenstate even for the torus, but I can write down other ground states. Yeah, in fact, I can write down 4 other states. And these are the states Vx acting on 0, Vx, Vy acting on 0, and Vx, Vy acting on 0. And it's kind of obvious they're eigenstates because Vx and Vy commute to the Hamiltonian. So this is an eigenstate, and these also have to be eigenstates. But you have to check that they actually are orthogonal. And the quickest way to see that they are orthogonal is that these states actually have eigenstates of the Wx and the Wy operators with opposite eigenvalues. So for example, if I take the Wy operator acting on the state 0, it's an eigenstate of Wy, at least at G equals 0. So Wy is a product of the Z's. All the Z's are just, let's see. What is the, let me just, yeah, well, it may have some eigenvalue, but whatever we know for sure is that Wy acting on Vx and 0 is the same as minus Vx acting on Wy times 0. So if Wy times, so if Wy times 0 is some phase factor you don't know times 0, then Wy acting on Vx0 has the opposite sign, minus y, minus eta acting on Vx acting on 0. So the eigenvalues of Wy are different between 0 and Vx of 0, and so they have to be orthogonal because Wy is an emission operator, and so on. So these are the other ground states. Now these ground states are not eigenstates of Vx and Vy, but it's easy to fix that. We can make everything eigenstates of Vx and Vy. That's just going to be equal to 1 plus or minus Vx, 1 plus or minus Vy, acting on 0. So those are the 4 states in a different basis. They have exactly the same energy at G equals 0. So now, of course, the question is, okay, that's great. You got this 4-4 degeneracy, but is it really robust? What happens when you turn on G? How is this going to lift the degeneracy between these states? And the important point is that at G not equal to 0, degeneracy is lifted only at order G over K to the power L, where L is the size of the system. And why is that? Well, you can see that just from this picture. So, if I look at the difference between this state and this state, how do they differ? Well, they differ by having, they're all sum over closed loops. There's various closed loops here but you have in this state, you have one extra loop that goes through the sample. So now if you want to mix them up, you have to flip all of these spins. And so you have to flip at least L spins by G that will flip the spin and get rid of that loop. That happens only out of G over K to the L. So in fact, there's a 4-4 degeneracy it's robust as L goes to infinity. It's exact when L goes to infinity at any fixed G over K, at least for small G over K. So if I look at the spectrum, yeah. Okay. Yeah. So the spectrum on the torus looks like this. I have 4 ground states. They may not be degenerate, but this spacing is G over K to the power L times K. Then all the other states have a gap at least of 2K. And then there's a whole bunch of states here. In fact, every state has a near four-fold degeneracy. And then there's a whole tower. But there's a robust feature here that the degeneracy is fourfold. So this is, when you think about it, a very remarkable feature of a system where the spins supposedly are fluctuating and are totally disordered. They're disordered, yes, but they seem to know something about the whole of space. They seem to know whether you're in periodic coordinate conditions or not. That gives you extra states at low energies. If you put it not on a torus, but higher genus surface, you get different degeneracy. So they're sensitive to the topology of the torus. And then you can write down topological field theories just for these states. And quantum computation corresponds to performing unitary operations on these states. And those unitary operations will commute with any local operator because these states have the same local structure. They only differ from each other from these global operators that go right through the system. Okay. I think that's really all I want to say. You can say, of course, a lot more, but that's the basic property, this topological degeneracy of this deconfined phase of the Z2 gauge theory. And this fourfold degeneracy is very robust. It still survives. You put the spin-ons back in, you put all the gauge fields, put matter fields, anything, it still survives. Unlike the area law perimeter law distinction that Wegener worked on, that doesn't survive when you add other perturbations. But this is a very robust signature of the existence of this fractionalization. Okay, so the final thing I want to say about this before moving on to other spin liquids is what happens at large G. Okay, so let's go to large G now. Any questions on the small G discussion?
I have a simple question.
Yes.
So when G equals 0, we have 4 topologically degenerate ground states on the torus.
Yes.
So are these ground states in one-to-one correspondence with the anion excitation before the ground? Above the ground state?
Yes. So you can think of this W operator. So you can also write them in terms of the W operators acting on the ground state. So you can think of the W operator as an operator. No, is it the W or the V operators? 1 second. Yeah, okay. Yes. That's a good question. So let me. Yeah, okay. It's a good way to say it. Okay, so suppose I have a torus here. Now I need to draw a torus. And here's a torus. And then what I do is I'm saying it's in its ground state. Then I want to get the other state, and I've shown you get the other state by hitting the V operator. Let's say I hit the V operator. So if I hit the V operator, I put the V operator in this direction. Let's call it the Y direction. So that's another state which I claim is, it's somewhere in this Hilbert space. Okay. Now, how does this operator differ from the original operator, original state? Now, in this new state, let me measure the value of Wx. So I'm going to take Wx, which will be on this contour. So I'll take Wx. in this way. Okay. In fact, I showed you then the eigenstate of Wx. This state will have eigenvalue of Wx, which is negative, which is flipped its sign as the opposite sign. So if I take the W operator as a product of Z's in this big loop, I get the opposite side. Now, what does that mean? Well, let's go back to the lattice. Remember, so what happens when I get a Vizon? When I get a Vizon or a quasi-particle, I have a -1 here. There's some line here. If I take the W operator here, the product of these Z's around this, I get a -1. Well, this costs me energy. Here, I'm taking the W operator on this big loop. I'm getting -1. So that tells me that in here, in the whole of the torus, there's a Vizon. So going from one ground state to the other corresponds to putting a Vizon in the whole of the torus. But that doesn't cost you any energy because there's no matter there. So there is a quasi-particle, but it's sitting where it costs you no energy. Okay. Yeah, so that's, and then depending on whether you put the Vizon in this hole or the other hole or in both holes, that's how you get the 4 states.
So the anion eigenstate corresponds to the eigenstates of the W operator.
Yeah, so there's, right. Well, if you're talking about Vizons, yes. And then there's a dual description in terms of the E particles, where you interchange the role of W and V. They are both equivalent description of the same Hilbert space. So to repeat what I said, if you have one ground state, that ground state differs from the other ground state by putting a Vizon in the whole of the torus. Another way to think about it is, we think of the V operator. The V operator is a product of sigma x, a product of x's, right? So the x's, it turns out, correspond to, I always get confused here, creating an E particle, yeah. What do the x's do? Yeah. So what this, you can think of the Vy as creating two E particles and taking them around the whole of the torus and annihilating them again. And that takes you back to the other state. So there's two different ways of thinking about it. You either put a Vizon in the whole of the torus or create two E particles out of the vacuum, take them around and then annihilate them the other side. So there is a close connection between the ground state degeneracy in the ground state Hilbert space and the quasi-particle. Of course, there's very beautiful topological field theory of all this for all the other states, which I won't get into. In fact, I'm not an expert by any means.
Okay, thank you very much.
Okay, great.
Can I also ask a question?
Sure.
So you said because of the periodic boundary conditions on the torus, so we get these extra states, right?
Yes. Well, I mean, of the extra state, there's certainly extra.
The extra constants.
Extra constants of motion, yes.
Okay. So what was the original? So the theory which is not on the torus, is it on the infinite lattice or is it on a finite lattice?
I was thinking in terms of infinite lattice, yeah. Because I don't want to worry about the edges. Yeah, of course, there's also very interesting effects on the edges, and you have edge theories, which are also highly non-trivial. But I don't want to get into that.
Okay. Yeah, thanks.
Okay, I think this may be a good time to stop because yeah, sure, I'm happy to have more questions. What I will do after the break is I will talk about, now that we have this technology all understood, hopefully within less than an hour, I will show you how you can get 3 or 4 other spin liquid states. But go on, question. There was a question, please.
No, it was just two comments on the previous person's question. So I guess if you don't have periodic boundary conditions, you can just introduce 2 types of boundaries, right? To condense each type of anion.
Yes, yeah, sure. Yeah, you can write down an edge theory and different types of boundary conditions, and yeah, and you can get either gapless states or not, depending on whether you have any symmetries. And if you get a gap, there's two different ways of getting a gap on the edge with the with which particle you condense, correct? Yeah. Yeah, that's not in the notes, but it will be in my book, all of that. Yeah, thank you for the comment. Any other comments or questions? Okay, we'll take a break then.
Okay, 10 minutes, let's do.
Okay, yeah. So today I don't have to finish exactly at 5. I can go over if needed.
Okay.
Yeah. Oh, you can see me. Okay.
Can I ask a question in the meanwhile?
Yes, please.
I was wondering if the robustness of this degeneracy of the ground states is a peculiarity of this model, or if we consider similar models, it resists, like we have the same feature.
No, I mean, I think the understanding is that anytime you have a model which is in this phase of matter, meaning, so how do you define the phase of matter? Define this phase of matter as having a particular set of anyons. So if you define a Hamiltonian, which in the infinite size limit, has fractionalization, has an E particle and an M particle, and with the same braiding properties, that E going around M gives you a -1. So if you have any Hamiltonian that has that phase of matter, then quite robustly, that same Hamiltonian on a torus will have the 4-fold degeneracy.
Okay.
Of course, if you have to prove that those anyons exist, but you can prove that in the infinite system.
Yeah, but I mean, also at a finite size, typically they start to overlap always exponentially in the size.
Yeah, so of course the size there has to be a gap, and the system has to be, size has to be much longer than the inverse correlation length. But as long as those conditions are satisfied, the degeneracy is robust. Yeah.
Okay, thank you.
I mean, it's not exact, of course, unlike in the toric code where it's exact. Here it's exact only at G = 0, but it's an exponentially small splitting. Okay, so I forgot, actually, we're not fully done with the Z2 spin liquid. I talked about the G goes to 0 limit, where you have the interesting deconfined phase. But now we're going to talk about the confining phase, which is as G goes to infinity. Okay, so at least for integer S, when this is 1, then actually that's quite trivial. When G goes to infinity, you forget about this. And so you just have to optimize this. That means you just put every spin pointing in the right direction. So, for integer S, then the ground state is basically unique, which has all the spins pointing in the right direction. Product on L, it's exactly that state. And unlike the G = 0 eigenstate, this is also an eigenstate on a torus. It's an eigenstate of Vx and Vy. So Vx times G equals Vy times G, which is equal to 1, because the eigenvalue of the X operator has to be exactly 1 when G goes to infinity. So, and that's it. So there is, if I make Vx equal to -1, then you pay a huge energy cost of 2 times little g. That's a huge cost, you don't want to pay it. So the ground state is unique, even on a torus. So the degeneracy is gone. And so this is a very different state. It's kind of a trivial product state. You can see now why we call it trivial. It's just a product. It's not the sum over all kinds of loops. There's no entanglement at all. And it's unique on a torus, so it's completely different. And just the fact that it's unique on a torus and the other one had a 4-fold degeneracy immediately tells you that between G = 0 and G = infinity, there has to be at least one phase transition. You believe that's the only one, but anyway. Okay, so that's easy disposed of, and that's the confining state. If you look more carefully at the excitations, you'll find that the excitations only have integer charge as far as the original XY model is concerned. So it's quite easy to establish that in perturbation theory in little k over g. Okay. But how about half integer s? That's much more non-trivial. The problem is that, well, I should have mentioned here, when all the x's are +1, then the product of x's is also +1, and this is easily satisfied. But what about half integer s? And the product of x's has to be -1. Okay, so now you're in trouble. You can't just minimize all the terms. If you minimize every term here, the product of this will be -1, +1. So at least one of the x's has to point in the left direction. Okay, so what's a possible ground state? Well, what you want to do is to make sure that just the minimum number of x's point in the left, point in the left direction. So you just have to pick one of these four. You could put 3 of the 4, but why pick 4? Why put 3? Because you'd have to pay too much energy then. You have to pay energy of 6g rather than just 2g. So let's say over here, I flip this spin, and let me color it. So this is x equals -1 on this link. Okay, so that link has x equals -1. And now that I flip this, I don't want to flip this, or this. So those are excluded. But I could flip this. I could flip this one, and so on. And you see very quickly what you have is dimer packing. Okay. So you in fact have a huge degeneracy here. It's an extensive degeneracy. It's exactly at g equals infinity. The ground state is extensively degenerate. Any dimer packing of the square lattice will give you a different ground state with exactly the same energy. Okay, so then you have to do perturbation theory. In k over g. So you have some, it's not like 4-fold degeneracy on a torus. This would be, e to the L degeneracy on a torus, where L is the size of a torus. But there's so many different ways of packing dimers on the square lattice or any other lattice. So when you do first order perturbation theory in K over J, you have to do degenerate perturbation theory. And that gives you some effective Hamiltonian. And that Hamiltonian is in fact precisely the quantum dimer model. So you have to solve a non-trivial model, which is the quantum dimer model, and find its ground state. And that's not an easy problem, although its lot is understood today. And depending on which lattice you're on, you get different ground states. And in fact, in some cases, the ground state of the quantum dimer model still has the topological degeneracy, still has Poisson excitations. So in fact, in this case, on certain lattices, all the way from g equals 0 to g equals infinity, it's in the deconfined phase. On other lattices, you could get crystallization of the dimers, and that's what's called a valence bond solid. So the fate of the quantum dimer model, depending on the lattice, it's either a Z2 spin liquid or what's called a valence bond solid, where the dimers crystallize. So this is a confining state. This is not a confining state. And so when you have this, it's this Vesumino-like term here, it leads to deconfinement. It can also give you a spin liquid all the way up to g equals infinity. So the topological degeneracy, for example, on the triangle lattice, it's believed that at least for certain range of parameters, you can go all the way from g equals 0 to g equals infinity and always be in the spin liquid phase.
Sorry. What exactly is this quantum dimer model?
What exactly is it? Okay, so I'll just say a few words, but I want to move on to other topics. Yeah, okay. So the quantum dimer model is a Hamiltonian that acts on the dimer Hilbert space. So if I give you give me a lattice, then I make a list of all the I make a list of all the states, I'll call them D, where D belongs to some dimer packing. So, if you give me a chessboard, I figure out, some huge number of ways I can put dimers on the chessboard, close pack them, and each configuration of dimers is a state in my Hilbert space. So I just label the states by configuration of dimers. Then there's a Hamiltonian that acts on the Hilbert space, and it has typically two types of terms. The interesting term, which will appear from K over G type correction, will be a term like this. It will be sum over plaquettes. And what it'll do is it'll take two dimers that are this way and flip them to the other way. Let's not here. In fact, that's the main term that appears at first order. So here's our Hamiltonian now. I have all these different dimer packings. And then I have some off-diagonal matrix elements. I can connect one dimer packing to another dimer packing if they're just related by taking two dimers and flipping them. So this is the resonating valence bond type picture. These are clearly some remnant of the singlet bonds I began my first lecture with. And this is the resonance. So now you have to diagonalize this Hamiltonian. It involves diagonalizing this huge Hamiltonian or exponentially large size. And people have, of course, done a lot of numerics on it. And there's also various kinds of duality transformations and field theories where that would take me too far afield. I'll just say that when you diagonalize a Hamiltonian like this, there's one, depending on the lattice and some higher order terms, the answer is either a Z2 spin liquid or some kind of valence bond solid. Okay, well, I hope that helped. I really don't want to say much more.
Yeah, thank you.
Okay, so now I'm ready to move on to something beyond the Z2 spin liquid after 2.5 lectures. And I'm happy to discuss more in the discussion session after this lecture. So the basic trick that we've used so far to construct the Z2 spin liquid is the Parton approach. And I'm going to make the table of different Parton theories and the different phases of matter that yield to us. So first, suppose forget about Partons, suppose I just had bosons. I have some lattice model of bosons moving around and interacting. What can bosons do? Well, the thing that bosons always like to do is they condense. So they can form a condensate, or they can condense, and that gives you a superfluid in the ground state. Okay. Another thing you can have bosons do, if the interaction is just right, maybe the bosons by themselves, like say hydrogen, well, hydrogen, I don't know, it's a boson. But anyway, for some reason, there are two bosons and there's strong attractive interaction between them. So it could be that the bosons would pair, form a molecule, and then the molecule, which is a boson, would condense. So you could also get a pair condensate. And there are various other possibilities, but I won't go. This is what we need for now. All right, so this is what ordinary bosons like to do. They could be a superfluid, they could also be a solid, but that's not so interesting. Or they could form a paired condensate, depending if the conditions are right. But now let me look at bosons, which are not just ordinary bosons, but which are partons of a spin. Okay. So when this happens, the bosons, in addition to being a boson, also carry a gate charge. And in this kind of decomposition, they carry a U1 gate charge. Okay. Now, suppose these bosons here, which carry a U1 gate charge, suppose they condense. So the B alpha condense here. So now if the boson just condense on their own, and now there's, this is like condensing the phi particle in the very first lecture. That carries a fundamental U1 gate charge. And there, condensing the phi particle gave you a trivial state. But here, the boson also carries a spin index. So it does give you a trivial state. The gauge typically are gone, but you've broken the spin rotation symmetry. So what you're getting here is antiferromagnetic long range order. This is like the long range order state. Okay, that's what you describe as spin wave theory and integer spin excitation and so on. But what about if you take these bosons and you condense them as a pair? Well, that's exactly what we did for the Z2 spin liquid. Q bar was epsilon alpha beta, U dagger alpha, U dagger beta is not equal to 0. That's a pair condensate. And that break, that gives you a Z2 gauge theory, and you got a Z2 spin liquid. Okay. All right, so that's what we've talked about so far. But now suppose I did the same thing, but with fermions. So now I'm going to do fermions. And in fermions, the floodgates open, because in many ways, fermions are far more robust, so far more versatile in creating novel phases of matter. So let's see. So let's first take ordinary fermions with no gate charges, with short range interactions. What can they do? Well, they can form a Fermi liquid. Okay. They can form a boring insulator, but not so. That won't give us anything interesting. They can form a BCS superconductor, ordinary superconductor. And I'm going to keep expanding this, but another thing they can do, which we're going to get to, is form a Churn insulator. So this is, this is a purely free fermion effect. If the band structure of the fermions has some Churn number, and they have a non-trivial quantum Hall effect, and they become a Churn insulator. All right, but suppose I did the Schwinger fermion construction. Okay. And now I look at the corresponding phases of fermionic partons, not ordinary fermions, but fermionic partons. The difference being that fermionic partons carry a gate charge. So what will we get here? Okay. So here, for a Fermi liquid, you'll get these fermions, we call them spin-ons. They just carry spin, they don't carry charge. And the spin-on from a Fermi surface, you'll get a spin-on Fermi surface. And you would also have a U1 gauge field. So you would have to then look at the problem of a Fermi surface, fermions coupled to a gauge field. So that's a very basic problem. It appears in the spin-on Fermi surface problem. It also appears in the quark-gluon plasma. And this will be the topic of my last lecture. It's a highly non-trivial phase of matter. In fact, it doesn't have any quasi-particles, although it does have a Fermi surface. And I hope to get to that by the end of my last lecture. So we'll put this aside. It's not a gapped state. It's a highly non-trivial gapless state of matter. Okay, well, but fermions, if they want to condense, can't condense on their own, unlike bosons. Fermions can only, but they can condense in pairs, just like here. So you could imagine a BCS condensate. And what does this give you? Well, amazingly, it gives you the same state. So this is something that took a little while to understand, but is now thoroughly understood. You can get exactly the same state. You start with some spin Hamiltonian. You can decompose the spin into the bosons, pair the bosons and get a Z2 spin liquid. Or you can decompose the spin into fermions, pair the fermions and get a Z2 spin liquid. What's the difference between them? Well, here, the bosons, after they condense, carry a Z2 gate charge, and they become the E particle of the Z2 spin liquid. Here, the fermions, after this condenses, they carry a Z2 gate charge, and they become the epsilon particle. So this gives you a theory of the epsilon particle. This gives you a theory of the E particle. They both have an M particle. And then you know that a bound state of an E and M is an epsilon. That which is what you do there to get the epsilon. And over here, you take the bound state of the epsilon and the M to get the E. And there's some very beautiful work by Ashwin Vishwanath and others showing that you get all the right symmetry signatures when you take two different approaches and you describe the same Z2 spin liquid. All right, so far, nothing new. Okay, so now we come to the new stuff. Now fermions can do other things. It could be that the partons, instead of forming a superconductor, the partons go into a Churn insulator. For some reason, the partons have some band structure, and that band structure is non-trivial. So what we are seeing now is an example of two different types of topology. And these are really distinct, and unfortunately in the literature, topology is used to describe them both. We had the topology of the Z2 spin liquid that had to do with the ground state degeneracy in a torus. Now we have a different topology, which is the topology of bands. And certainly in the literature now, in condensed matter literature, that's what topology is. It's a topological band structure. It's a very different topology from that here. But in the Churn insulator, we're combining both. We have a gauge field from this decomposition. In fact, it's U1 gauge field. And they fermions form a Churn insulator. So they don't condense, they just fill a band which has a Churn number. And this leads to over here, something I'll describe now in a few minutes, the chiral spin liquid. Okay. So this is a new state of matter. It's another spin liquid with different anion content and different degeneracy on a torus. It's got anions, unlike the Churn insulator, which has no anions. Here, because of the gauge field, we have anions. And the topology of the band structure of the partons gives you a different state of matter. Okay. And let me, under the table in your notes of many other states, I do want to mention a few of them before I give you, since I might run out of time at the end, I'll make the table and I'll describe what I can. Yeah, so I just want to add one more, and so I'll do that over here. I'll continue this table. Well, actually, I want to add two more, or well, maybe more than that. Yeah. Okay. So I want to add another possibility, and that's called a topological superconductor. Again, I use the word topological advisedly because it's band topology, nothing to do with anions. And it's a P plus IP superconductor. So what I mean by this means that, first of all, the fermions pair, but they pair in an odd parity state. And there's a lot of spin orbit coupling, so you can just forget about the spin index. So it's a P plus IP superconductor. And the feature of the P plus IP superconductor is that its Bogoliubov quasiparticles have a Churn number. So what I mean by this more precisely is the Bogoliubov quasiparticles have the Churn number. The dispersion has a Churn number. Okay. All right. So there's a lot of experimental search for such materials. Some odd parity superconductor, where because of the spin-orbit coupling and the band structure, the Bogoliubov quasiparticles have some non-trivial Berry curvature. Okay, so that's ongoing. There isn't any convincing example yet, but there's a lot of promising searches of that type. On the other hand, if I take a spin system and I decompose it into fermions this way, and then the fermions, the Fs, and this requires spin-orbit coupling here too, the Fs form this state. So that means effectively, once you've paired the fermions, you have a Z2 gauge field. And so you take a topological superconductor and you couple it to a Z2 gauge field. So here you would get a P plus IP superconductor. Plus a Z2 gauge field. Just like the one we've been dealing with. So the only difference between everything we've talked about in this lecture with the Schrödinger bosons and the coupled to Z2 gauge field is that here you have fermions. And the fermions have some funny stuff in their band structure. That's all. But it's exactly the same theory I wrote down at the beginning of the class for Schrödinger bosons, except you replace the bosons by fermions and you put some funny band structure corresponding to this. And the precise, it's not in the notes, but you can find it in many places in the literature. So this turns out to be a new phase of matter. And this is the Ising anion phase. It's non-abelian Ising, non-abelian anions. It's not a Z2 spin liquid. And it's also the exact solution of the Kitaev honeycomb model. But you don't need the exact solution. It's a phase of matter, which will occur anytime you have a Z2 gauge field coupled to a topological superconductor. All right. I don't think I'll have time to talk about this. That's a bit complicated, but it's really, you turn the same crank that we've been turning for all these other phases. And this is another phase that, ruthenium chloride is a compound which many people are now studying, which possibly in this phase, although I would say at this point, the evidence doesn't look very good. Okay. And let's see, maybe I'll have time. Let me also make a table here similarly for the quantum Hall states. Fractional quantum Hall state is another place where you have interesting things happen. So, So if I have electrons, and then in the magnetic field, they can do some funny stuff. And then you have fermionic partons. So here, it turns out the best way to do this, you have an electron operator. This is not a spin system, so you have a fermion, but you make partons of it. I'm going to make 3 partons. You can't compose a fermion into 2 partons, because then it would be a commuting operator, but you can compose a fermion with 3 partons. All right, so this is just one step beyond the composition here of 2 partons. You go one step further, you compose it to 3. All right, so what can electrons do? Well, electrons in a magnetic field form an integer quantum Hall. So if I take these 3 partons, if all of them, F1, F2, F3, form integer quantum Hall states, then if I put the gauge fields in here, which hopefully I have a few minutes to talk about, you will get the Jane and the lawful states. So it's, really as simple as that. You take electron, split it into 3 partons, put each of the 3 partons in an integer quantum Hall state, and you'll get essentially all the observed fractal quantum Hall states in the appropriate gauge theory of this decomposition. Then you can do other things. You can take the first fermion, F1, and have it form a P plus IP superconductor. This can happen at certain filling fraction if the net field on F1 is 0. And then F2 and F3 form the integer quantum Hall state. And this leads to the Moore-Reed non-abelian fraction quantum Hall state, which, there's some sign of in some experiments. Okay, so that's pretty much it. So once you get comfortable with this parton theory, parton approach, you can just work out all of these cases and pretty much exhaust all the possible exotic gap phases of matter that are being studied these days, or have appeared in numerics or some experiment or the other or something like that. So it's a very, very powerful approach. And in fact, I think it's the best approach for understanding what's going on. It just requires you to understand a little bit about the dynamics of gauge theories, which is why I spent 2 lectures on that. Okay. All right, so that's just and there's no way in 20 minutes I can cover all of this, but I will try to show you. Actually, it's quite simple. Now we have almost all the tricks in our bag to figure all this out. Yeah.
If I have a quantum fractal spin system, in which category I would put it?
Well, I don't know. First I would ask is, what do free fermions do in a fractal? And then I would start from there. Once I know what free fermions do on a fractal, then I would couple that free fermion system to gauge fields and then ask what kind of topological phase I get. I don't know. It depends on what the free fermions end up doing. If there's a gapless spectrum, then I don't know, there'll be probably some variation of the spin-on from gapless state with the spin-on Fermi surface.
If they are gapped in bosons?
Well, bosons just tend to condense. It's very hard to stop bosons from condensing. Either they condense and you have long range order, or you have a pair condensate, and that's about it. That's, the possibilities with fermionic partons is much richer. It allows you to do many more things because fermions, once you put in the topology of some band structure, they can do a lot of interesting things.
Thanks a lot.
Okay, so let's talk about this. Yeah, all right. So what happens here? Okay, so I just follow this route. I do this decomposition, and I'm going to put these fermions in the Churn insulator. Okay, so what does that mean? That means I have some Hamiltonian for the fermions, which have some rather complicated band structure. Some of I less than J, Tij, F dagger I, Fj, there's also a spin index, and that's it, okay. Plus some, this includes on-site, well, minus some chemical potential terms of which F dagger or lambda, let me call it lambda. Okay, so they don't pair, they just have some complicated band structure, and this Tij has to be determined from saddle point value of some action that we, at least wrote down for boson, although I didn't do any calculations. And this kind of theory I have to now take this Churn insulator. So I assume the Tij are such that there's a non-trivial Churn number. So there's some band. So we get function of K. There's a band here, there's some other band there, and these are filled. My chemical potential is over here. These are filled, those are empty, and this has some Churn number. And in fact, I want to take Churn number 1. Okay, so that's the mean field state. Filled band with Churn number 1. And that's it. That's what my fermionic partons do. I take my spin, I split it in 2 fermions, and just put them in here. And the counting all works out. I have to have a constraint that F dagger I alpha, if I alpha equals 1 on every side. And at least in mean field level, you satisfy that because this Tij is such that you double the unit cell by the phase factors and get a Churn number. You know, it's like a Hofstadter problem with pi flux will look at. Okay, now you have to look at fluctuations. This is where couple this to a gauge field and you're going to get some anionic state. And what happens then? Well, you put in a gauge field here. That's how it has to couple. There's a U1 gauge field. And I think I can delete this. Okay, so we're talking about this. The others we've already discussed. Okay. So I have these gap fermions and they're coupled to a U1 gauge field. So what I want to do is to take my theory. I have a theory like this, the dA of e to the minus some Lagrangian, which is given by this Hamiltonian. And I want to integrate out the fermions because they are fully gapped and they're sitting over here. I'm going to get dA of e to the minus some L effective of A. Okay, so I have to just do the one loop calculation here. At one loop order, I'll get some quadratic term dA, couple like this. So you just have to integrate out the A's and figure out what you're going to get. All right, so and there's also a sum over spin. Okay, so what you get here is the following. This gives you at leading order a Chern-Simons term. And the coefficient of the Chern-Simons term is plus I times the Churn number over 4 pi is a factor of 2 for spin, times epsilon mu mu lambda A mu W A lambda. So this Churn number C, because of the Churn number of the fermions, you end up getting a Chern-Simons term for the gauge field. So this is rather different from the Z2 spin liquid. In the Z2 spin liquid, the gauge field became Z2 from U1. Here it remains U1, but it's U1 with the Chern-Simons term. Okay, so that Chern-Simons term changes the dynamics of the gauge field. And I don't want to go into those details here, but it's it's not that complicated. Maybe that can be topic of some. Maybe in the discussion session, if people are interested, I can say a bit more. So what the Chern-Simons term does is it takes these fermions. So, what are the excitations of the system? Well, the excitations, you could add a particle here, or you could make a hole here. So you have these fermionic particles that are initially fermionic. But these particles couple to the gauge field, and the gauge field has a Chern-Simons term. So what happens when you take the fermions around each other, they pick up a phase factor. And because of this factor of 2, the C is 1, what happens is that the fermions, under the influence of the CS term, become semions. Not neutral semions, but that means if you take a fermion and exchange it with the other one, you get a phase factor of I, not -1. So this thing breaks time reversal symmetry. You either get I or -I, depending on the direction time reversal symmetry is broken. So Tij do have to break time reversal. I mean, you had to get a Churn number. And that's what the chiral spin liquid is. So it's a theory of a stable phase of matter. of spins, and it's been seen in numerics of some spin models, where the excitations have spin-ons, and the spin-ons are mutual semions. And that's it. There is no Wison, there's no E, M, and epsilon. There's just a semion. It's the simplest, non-trivial anionic phase that breaks dynamical symmetry. It has a two-fold degeneracy on a torus, not four-fold, and so on. Okay. But that's, that involves going into understanding a little bit about the dynamics of the Confining theory. Okay. So that's how you get the chiral spin liquid. That was very quick. Apart from, I'm assuming, of course, you know what a Churn number is, but I suspect you all do. Okay, questions? Okay, so you're all there, right? That's quiet. Someone say yes.
Yes.
Okay, thank you. All right, so now let's go to the quantum Hall effect. Why not? Okay. So we're going to a slightly different parton decomposition, but you'll be amazed how quickly and how easily we can now get the theories of all, at least of all the Laughlin and fractional quantum Hall states. All right, so let me just first discuss this parton decomposition a little bit. So let's put it on a lattice. So imagine we have a lattice. Okay. And on each side of the lattice, I have a spinless fermion. Okay. So there's two states. There's the empty state, and then there's the state with the fermion on it, the fermion called C. So this is the physical fermion, the electron that's going to form a fractional quantum Hall state. Okay. And then, of course, I'm going to put a magnetic field on the lattice and so on. But for now, let me just do some parton trickery. Okay, so now I'm going to think of these two states. The vacuum is going to remain the vacuum. And this particular state, I'm going to state, has three fermions in it, F1, F2, F3. Okay. So I'm going to take three partons and allow them to sit on that side. If I have three fermionic partons, there's a total of 8 states, because either of them can be empty or occupied, 2 times 2 times 2. But only 2 of them are physical, in this state and this state. So I want to reduce my Hilbert space from 8 states down to 2. How can I do that? I just need 2 constraints. I need the constraints F dagger 1, F1 is always equal to F dagger 2, F2. And I need the constraint, say F dagger 2, F2 is equal to F dagger 3, F3. So if I just impose these constraints, these 2 constraints, they're sufficient, then immediately these constraints are only satisfied on these 2 states. They're satisfied on the empty state, and they're satisfied on the occupied state. And they're not satisfied on any of the 6 other states that the partons can create. So, and this is just the analog of what we did for the spins. You only allow this 1 Schwinger boson on each side or 1 Schwinger fermion on each side for spin I have. And then you project it out the others by a gauge field. So here you have 2 constraints. And so that means you're going to have a U1 cross U1 gauge theory. One U1 here, another U1 there. Okay. So just a little bit more complicated than what we did, but not too much more. Okay. So the root is pretty much the same thing, that you think of the partons as free particles to begin with, and then you couple them to a gauge field. But you want to have the partons be free particles in some nice band structures. Here we had a band structure that had a gap, and so there's an insulator, because once your partons have a gap, then it's a possibility of starting out from some stable state. Okay, so let's see what we can do here. So the electrons, to begin with, are in some magnetic field B. So I have some action for the electrons. the electrons experience some grad minus I A. Let's see. Write it down nicely. Yeah, okay, well, I haven't written it out. All right. So there's some physical magnetic field that the electrons experience. All right. So now I can put that physical magnetic field to act on either F1, F2, or F3. It doesn't matter much. So let's say I put it on 1. And then I have 2 gauge fields. I have one gauge field as of this constraint, and another gauge field as of that constraint. So what will I get? What will be my free particle Hamiltonian for these partons? So I have F dagger 1. Let's say it experiences the physical gauge magnetic field. It's all acting on F1. But then there's a gauge field that imposes this constraint, which I call A1. And then F2 will have the opposite sign of A1, because when you do a gauge transformation, if you do transform this by one factor, this has to have the opposite sign. And similarly, there'll be another gauge field A2, which has one sign here and the opposite sign there. So I'll have a minus A2. Plus F3, which will be right, plus 2 squared acting on F3. So I've taken my theory of electrons in a magnetic field A and converted to a theory of 3 fermions, and with this field here A, and also these different gauge fields. Okay. So now I want to deal with the, start with some saddle point. And the key here is that these internal gauge fields can also have a net non-zero magnetic field associated with that. And that I can use to my advantage, because I want to be able, I want to put all of these partons in fully filled Landau levels. Okay. Just like for the integer quantum Hall state, I want to put F1, F2, F3 in IQH, meaning they must occupy some Landau level fully. And so that's kind of what I want to do. All right, so now let me define the field that acts on this particle. So this tells me, I call this B1, is del cross A plus A1. And B2 is del cross A2 minus A1. And B3 is del cross A2. I hope I have the signs right. Minus sign, so this is minus. It should be minus, okay. Yeah, okay. And you can see from here, and of course here, I have B, I'm going to call B is del cross A. So I have the constraint that B1 plus B2 plus B3 equals B. Okay. So that's one constraint. All right. So this, where here, this is the expectation value, average value. So these A's are fluctuating, but now these are the average value. Okay. Okay. So now what do I have to do? I want to choose B1 and B2 and B3 so that to choose so that F1, F2, F3 occupy N1, N1, N2, N3 Landau levels. So this gives you some constraints because of the structure of the Landau levels. So that tells us that, so the density, so now we have some density. So the density of fermions, rho, is the density of C, F1, F2, F3. They all have the same density because every time there's a C, there's an F1 and F2 and F3. Okay, so this will tell you that N1 is the density rho divided by B1 over phi naught, where phi naught is the flux quantum. That's the just from the counting of the number of states in the Landau level. N2 is rho over B2 over phi naught, and N3 is rho over B3 over phi naught. And then the filling fraction, which is nu, that's the way it's called. So the filling fraction for the fractional quantum Hall states, nu is the same, rho over B over phi naught. Okay, so now you take all these relations, N1, N2, and N3 are integers. They can be even or odd. And you have all these relations between N1, N2, N3, B1, B2, B3, and this one. And you put it all together and you get the global relation, which is like here, 1 over nu, the filling 1 over nu, the filling fraction is 1 over N1, that's 1 over N2. So what we have shown is that if you take an electron and split into 3 partons and then couple it to a gauge field and look for a saddle point, you want to look for a nice saddle point which has a nice gap. And with the parton, that means the partons have to occupy an integer number of Landau levels. So there's some 3 integers, N1, N2, and N3. And then if we just count the total number of states and the effect and the number of states available at a Landau level, you come up with this constraint. So if you could choose, if you can find 3 integers that obey this relation for electrons filling fraction nu, then there's a possibility of getting some non-trivial state of matter, which has a gap. Okay. Now you can, of course, look at fluctuations that are about this state by looking at fluctuations of the gauge fields about this state. And that gives you, a whole bunch of Chern-Simons terms, which are a bit more complicated than a chiral spin liquid, but we can work it all out. It's not that bad. It's just many different Chern-Simons terms if you keep track of all the matrix structures. But this, it turns out, this construction gives you a complete description of, I think, essentially all states that have been seen, at least at odd filling fraction. In particular, the most important ones are the following. The most important states are the Laughlin state, which is N1 equals N2 equals N3 equals 1. They're all 1, that you immediately get the Laughlin state. You can even see that at the level of the wave function, which maybe I'll say a little bit about. We're running out of time. And the Jane states are essentially, so the Jane states are N1 equals N2 equals 1. And let's say N3, some other integer, the positive or negative. Let me call it little n. And then you just solve this equation, and then you find nu is n over 2n plus 1, which is exactly the fractions, the most famous fractions that you see in all the fractional quantum Hall experiments. Actually, you can also take minus n, that's nu over 2n plus minus 1, something like that. So you get all of the Jane fractions. And you can, if you look at the fluctuations in the Chern-Simons term about the saddle point. That's the easiest way to understand all the quasi-particles, their statistics, the edge states, all of that just follows just by turning the crank from this particular parton saddle point. Okay, I think I will stop there for today. And tomorrow we'll start a very different topic on gapless states of matter without quasi-particles. Okay, I'm happy to have questions.
Okay, now. Thank you. Thank you, Subir.
Okay, questions?
Excuse me?
Yes, please.
I'm wondering why we're motivated to split fermions into 3. Why not 5, for example?
You can do 5, and then you get more some of the higher fractions. I think like the 1/5 state, if you want to describe the 1/5 state, you have to split it into 5. You can.
But they are all observed experimentally.
The 1/5 is seen, yes. I mean,
okay.
What happens in real world is once you get to very low fractions, then they form a Wigner crystal and not a fractional quantum Hall state. So that's just an energetic issue. But the most common, the most robust ones are these, the Laughlin and the James series. But there's another possibility which I write here, this one. So what can happen? So to get this state you get when you take N1 equals N2 equals 1, and you take N3 going to infinity. Meaning that when N3 goes to infinity, that means B3 goes to 0. And so one of the partons is in 0 magnetic field, and therefore it can form a superconductor. And that's when you get the non-abelian state. So that's a little bit more complicated. It's the cousin of the Ising anyon states or spins. But it's also very much the easiest way to understand it and is by this approach. And you can get all the statistics correctly in a few steps. Yeah, okay. I mean, I had learned of this from Mike Levin at some point, and I struggled so much with trying to understand the quantum Hall literature. It's just so confusing. And at least in my opinion, it took a while for people to understand this is the right way to do it. But once you see it this way, you never do it any other way, really. It's much cleaner.
I have a related question. So the number of, this F particles fermion fractionalized into, is this somewhat related to the integer m in the Laughlin state?
For the 1/m states, yeah, that's correct. If you just want to describe the simplest Laughlin state at 1/m, then you will need m partons, correct? And I can actually show you why. It's actually very simple. So there's a focus argument. You can do this, but there's even a simpler, well, actually, yeah. So suppose I take, so the first thing I want to tell you is that if I have a fully filled Landau level, of electrons, then the wave function of a fully filled Landau level is the van der Waals determinant. This is the determinant of 1, Z1, Z1 squared, and so on, Z1, Z2, so on, which is just product on I less than J, Zi minus Zj, and some exponential factor I won't worry about. Okay, so this is a fully filled Landau level, Zi minus Zj to 1. Okay, so now if I take partons, I take m partons, and I'll put them all in the lowest Landau level. Okay, so I have partons. I have parton 1, so, and I look at their wave function. So F1 goes into lowest Landau level, and F2 goes into lowest Landau level. And this has, say, some coordinate, I don't know, ZA, this has coordinate ZB, and so on. But then you have put it a constraint. The constraint that have to have the same coordinate because they have to be exactly the same point. And so these all equal, ZA equals ZB equals ZC equals Z. So the wave function of the parton is the product of the wave function of each. And each parton has one factor of Zi minus Zj. We take m partons and you just get a factor of m. That's all. So this is just an observation that you can take the product of m lowest Landau level wave function, each having a weaker magnetic field because of this constraint that takes care of the exponential factors if you do it right. It just gives you the factor of m. Okay. And then if you want to do it for other fractional states, then of course you're not in the lowest Landau level, and that was the idea that Jane introduced, that you should take these partons and put them in higher Landau levels and you get all the states that you see. Yeah.
Okay, thank you very much.
Sure.
Okay, I don't know if there are other...
Can I ask something more?
Yeah, go on.
I wanted to ask something about the Zeta 2 gates theory and the duality with, okay, the Zeta 2 gates theory is dual with the transverse field Ising model.
Correct.
But we have the Zeta 2 gates theory, and we can express it via this finger representation in terms of bosons or fermions. In every kind of this representation, I have a very phase term that comes into play. Sometimes this very first term restricts this duality, right? I mean, sometimes this very first term as a fully quantum term cannot allow a duality between a classical and a quantum model. Is this true? Or when isn't true?
Okay. I can answer the last part of the question. First, so it's often true that when you take from a quantum model and write it as a classical model, the classical model has non-positive weights. So it's not a person in stat work would naively think of because the weights are not all positive. That happened here or happened in the spin. I took the gauge theory with this constraint. You take a Z2 gauge theory with Gi equals -1. When you write it, when you perform the duality transformation, actually this one, well, when you write the path integral, there's a phase factor, which is weight is not positive. However, when you do the duality, you get, in fact, the duality still works. You get an Ising model, which is fully frustrated when the product of J's are on the plaquette. And the dual model is -1. And in fact, that was actually the first place that I discovered this factor that I presented in this language. Okay, but the other question was you want to...
There are some models. Yeah, there are some models that when you have this very phase term introduced, there is no duality between a quantum and a classical model. Like this very phase term doesn't allow this duality. Could we say, like, by seeing at first a model, if the very phase term would restrict us and don't allow us to have a duality? Or is it like I check all these terms and see if the phase transition, for example, observables are matched?
Well, I would rephrase your question a little bit. I mean, you're equating duality with quantum to classical. That's not, I don't think that's the way most people use duality. You can have a duality between two quantum models. And you can certainly have a duality of, some fermionic model with Berry phases, and that's dual to some other bosonic model with some other Berry phases. The two quantum models. So that's one. Yes, you can have those type of dualities. But I guess your question is, can you, by some, like the Z2 gauge theory is dual to a transistorializing model. But you can also think of the transistorializing model as a quantum model, but it's also a classicalizing model. But I agree that if you take Z2 gauge theory with matter, then dual representation becomes very complicated with highly non-local Chern-Simons terms, which are not classical, for sure.
Okay, thanks a lot.
Sure.
And maybe a more general question. So in spin liquids, like so frustration is an important say ingredient in causing the fractionalization. You also mentioned that because there are even theorems stating that there simply cannot be a trivial ground state. But what kind of is the fractionalization, like a mechanism for in quantum Hall system or charged liquids or Hall liquids? Okay.
Well, here is, you have a partially filled Landau level. You have a partially filled Landau level. There's a huge degeneracy of states in terms of the electrons. But when you fractionalize it, as you saw here, the degeneracy disappears because you get fully filled Landau levels with the partons. So it's some efficient way of, once you have partons, you can get states with a gap. And states with a gap tend to have lower energy. I mean, I guess we like to think. So yeah, that's what I would say. So here, you know, in this example, and also in the chiral spin liquid, you're using the topology of the band structure. Here you have the topology of the Landau levels or the topology of the Churn insulator to open up a gap. And the point is that when you fractionalize, then even though your parent, the Churn insulator, for example, even though your parent Hamiltonian may not have any topology, when you fractionalize, you have a degree of freedom. You have, like here, you have a degree of freedom of choosing the magnetic field. Or in the chiral spin liquid, you have the degree of freedom of choosing the Tij. So you have this new degree of freedom that you can exploit, that's available to the partons, and that can open up gaps in various topological band structures. So that's why you want to fractionalize, yeah. So in addition to frustration, you know, the point is that the partons can be moved in complicated band structure and complicated magnetic fields, and that you can use to your advantage to lower the energy. I think that's pretty much the principle that's operating. Yeah.
Thank you.